And we are back for the final show of the week. And yes, today is one of those days where we're going to have a live demo at the front of the room. Hopefully should be a lot of fun. So we've built up a little more C programming techniques now. We have malloc, dynamic memory allocation, and we have structs. But you still might be asking, okay, so I've got all this stuff. What's it all good for? Well, I've got someone who might know the answer. So as many of you might know, Taylor Swift is on tour, and this is very, very important. Have any of you managed to get tickets? Are you flying across the world to see Taylor Swift? Anyone? I'm the only person? That's a little disappointing. But you know, I'm pretty busy here in FOA, and so I'm not going to be able to actually use my tickets. And so we might do a bit of a ticket giveaway, full flights or accommodation included. But I need to figure out how to distribute these tickets. You know, I've only got a few of them. I've only got a few airline tickets. Josh put his hand up first. So should it be first come, first served? Do you think that's fair? Should Josh get the Taylor Swift tickets? I see some yeses, I see some nos. So this was our first option. Josh put his hand up first. He should get the tickets. Josh was the only one thus far, and I have more than one ticket. So does anyone else want a Taylor Swift? Bronson wants a Taylor. Dux? Giovanni wants to, Max? Okay, well, now I can't handle it. We're going to need a data structure to handle how I'm going to distribute the all expenses paid FOA trip to Taylor Swift. Now, if this does indeed go ahead, I'm expecting really good feedback on the end of semester survey. You can write about how good the show was. So we need a data structure to represent all these people, because I certainly couldn't keep track of who was putting up their hands when. So let's try option one. So I need all the people that I said were coming down today to actually come to the front. And Leo, you are going to get where are you? You are going to get this beautiful helmet here. Leo is going to be our computer for the day, who's going to determine how we allocate the tickets. So everyone come down. And so we said we're going to do first come, first serve. So how does that normally work? How does first come, first serve work if I'm distributing something? OK, so we have one person there. This doesn't look like a data structure. Could you organize yourselves, please? A line. OK, what's another word for a line? Queue. A queue. OK, so we're going to be talking about queues. And how does a queue work? Let's say this is the front of the queue. Leo, who should get the ticket, the first ticket? Okay, he's the first one in the queue. Okay, so hand over the Taylor Swift ticket. Now what happens? You just keep standing there? You've got your ticket. What do you do? You've got your ticket.
Got my ticket.
What are you waiting for?
I can leave. I can get out of here.
Okay. Stay near, close by, though, because we will need you later. Okay, now what? Well, what happens to the queue? What happens when the first person leaves? Let's give you a microphone. Okay, so what happens? The person at the front has left the queue. What does the queue do now?
I will form a new queue without him. I would just delete him. And
okay, we'll delete him. Now what happens to the queue?
Then the first one is you.
Josh, okay, so you're at the front of the queue now. The ticket window is here. What are you going to do?
You ask me now?
Yeah.
I'm going to move up to the first
Okay,
spot.
move up. Okay, now what happens to the rest of the queue?
Move up.
Okay, let's move up. Okay, now what?
And now, like, if I got another ticket.
Yeah, we got another ticket.
I would just give it to you.
Okay.
First one.
What are you waiting for?
Get out of here?
Yeah, get out of here. Okay, the queue moves up.
Yeah, queue moves up, and I just give away the next ticket.
Okay.
Okay, then the next.
And we're all out of tickets. I'm sorry, Nadine, you were just too late to class. Okay, back. And now everyone, let's reform the queue from the way it was originally. Okay, so we could represent our queue a few different ways. Option one is an array. Now let's imagine we have, Nadine, do you want to leave for a minute and pretend that you're coming late to class again? Just stay there for the minute. We have an array of 1, 2, 3, 4 elements, and let's say we do have a fifth slot available. So now Nadine has finally decided to grace us. What do we do with her?
I put him inside the list, into like the last spot.
Well, this is an array, right?
It is an array.
So, and this is location 0, 1, 2, 3,
So 4.
4,
Sorry.
yeah, 4 is after 3. And so what do we do with Nadine?
I put her in this 4th.
Okay,
like
yeah, you can
number
join the
4.
queue now. Great. Okay, let's try thinking about the same thing with what's happening with our array when we're taking people out from the front. Okay, so what do we do with Oliver?
So first, I take Oliver out.
And we access
take it.
which element in the array?
The zeros element of the array, and I take it out.
Okay, so our 0th element can go off. But now what's this? This was the 0th place in the array, right?
Yeah.
And so what do we have to do if we want to change where the front of the queue is?
I need to update the array, so I just move the first element of the
So let's say
array
we
to the
copy
0.
Josh. Unfortunately, is there another Josh somewhere here today? I know we do have 2 in the class. Darn, that's what I was hoping for, is that we'd have a copy Josh. Anyway, so there's Josh there and there's Josh there. Now what do we do?
And now I put the second element
It's
to
Dux.
the first.
And so we copy him into there.
And the
There's a second
third
Dux,
to-
right? Yeah, he's still there, okay. And your name again was Xian. Okay, so now we copy you,
her too.
and we copy Nadine,
Yeah.
and then we have a second Nadine who just waits there until another student comes along. Okay, so this seems to work all right, but it takes an awful lot of work, doesn't it, for us to like, every time we take someone out, okay, Josh, we'll give you your ticket and you can head off. And now we have to do the copying over and over again. So let's do that one more time. Copy, wait, leave your copy there, put your hand out, there's a copy. No, Dux, that was your copy. Yeah, Xian, now, yep, and now we do one more copy. You know, this is an awful lot of work for something that should be a lot simpler. Maybe if we just keep track of where the front of the line is, then we can update where the front of the line is, where the back of the line is. In fact, I've got another idea. Okay, everyone come back. And now, in fact, you can step out a little bit, go somewhere nearby, but take a step in some direction. Everyone, Oliver, let's keep you in front of the camera so that and the room can see what you're going on. Okay, now everyone point to the person behind you in line. That looks a little better. Okay, so let's set this up like our C computer program, and I'm going to give everyone a way to point to the person next to you. Okay, take a cable and pass the other cable on. And take a cable. And I have a few plugs as well. Okay, I have plugs and I have my arrow. Okay, Leo, do you want to come out here?
Yep.
And we can give this to Oliver. Actually, you know what? You hold that for the minute. You hold that for the minute, and let's point it to the front of the queue. Okay, everyone got a cable? Yep, except for Oliver. Now Josh, do you want to give Oliver the front of the thing? And now let's plug everyone together. This is starting to make sense. Yep, plug it in. Oh, yeah, and Dux, there we go. There we go. And let's make sure we have one of these nodes at every location. So I'll give you a node to start off. And now you can spread out more, go wherever you like in memory. We've got a lot of memory here. Josh, you probably want to stay in front so that everyone else can see you. So let's spread out this direction. Let's spread out, spread out, spread out. Right. And now we have our linked list. Let's imagine that every one of these spaces is a different location in memory. Now people can stand wherever they like and still form a queue. So now let's figure out how our queue works. Leo, do you want to give me some instructions? So let's disconnect Nadine, and she can be late to class for the 5th time today. Right? Okay, first thing that happens is Nadine shows up and joins the queue. How do we do that?
I would let my last node connect to her.
Okay, wait a minute though. We don't know where this last node is yet. He's scattered somewhere. So how do we find the last node? You've got an arrow that points to the first node.
I need to go from very first node, and then I ask.
Okay, so what are you connected to? Ask Josh.
Yep. Josh, where are you connected to?
This thing.
This thing. Okay, I'll just follow the green line.
Okay, we're following the line.
And hello, what's the next person you
Yeah,
can
follow the red line.
Okay, I'll just go third.
Remember to speak loudly because we're low on microphones today.
Right, so I find it that this is, I'm very sure that this is the last node.
That's the last node? Okay, so now what do? We know where Nadine is.
I connect Nadine using this line to the original last node.
Okay,
I get it.
and how many steps did that take us?
I think it takes 1, 2, 3, 4, 5.
Yeah, it takes as many steps as there are people to add someone at the end because we've got to go all the way from the front, go through every node, and go until we get to the end, and then pop Nadine on at the end. Okay, now let's try our other operation. What was the other thing we needed for a queue to work? So we know how to add things to the end. What's the other thing we want to do?
Maybe delete.
We wanted to be able to take things away from the front to give him our tickets. Okay, so let's figure out how this one works. You've got your arrow, and your arrow is pointing at the start.
So I distribute the tickets.
Yeah.
I just take you away, and I.
Wait, okay, so Oliver, disconnect yourself and go off wherever.
Okay. So now.
Wait. How did you get there? We destroyed the link 2 seconds ago. Okay, you'll have to come back.
So maybe I just ask him like, what's your next person, and I just change my settings to point to the next person.
Yep, and now what do you do?
And now, like, he becomes the first element in the node.
Yep, now Josh is the first element, and what do we do with Oliver? He's free, right? Malloc and free. Okay, you're free. And how many steps did that take us?
I think it's 1 step.
It just took 1 step. We followed the path once, and then when we were done, we let Oliver go free, and then we're good. Okay, so we've given away 1 ticket. Now let's do this process again.
So I need to give another ticket?
Yeah, you need to give another ticket.
I'll give you a ticket, and then I just notify the next node.
Yeah, we had to ask Josh what he's connected to.
Josh, who are you connected to this? Okay.
Follows. We get to another location in memory.
And I get, another location.
Okay, so now our pointer, our head pointer, the thing that points to the head of the queue or the start of the queue, is pointing to Dutch. And what can we do with Josh?
I can just free.
Yeah, we can free Josh. Okay, and that took how many steps again?
1 step.
1 step.
Okay, so now I'll give the ticket to Dutch, and then I ask you, like, who you connected to? Yeah, and I get to receive that cheer story. And I just free Dutch.
We free Dutch.
And this is also just 1 step. And finally, I ask your who you are connected to, and I follow the line, and I go to
Nadine.
Nadine. Yeah, sorry, I'm bad at this. And now I can free.
And then we're left with only 1 element of our list who's still, or our queue, who's still waiting there. Great, okay, so let's reconnect everyone 1 more time. And let's try for 1 more operation. So now we know how to add things to the back and remove things from the front. And this is pretty much all we need for a real life queue. But sometimes people don't behave like a queue. Sometimes people behave more like a, let's just say, a line where people come and go and push in and leave. And that's what real life is like. So let's try one of those. Now let's say Dutch has had enough of FOA. He doesn't really like Taylor Swift. He's a big Jay-Z fan. And so he's going to leave the line. But we have to find a way to get rid of him. Okay, so let's go through this process. We know that the person we're looking for is Dutch, but we don't know where in the list he is. He's going to be somewhere. So let's figure out, first step to remove him is to find him, right? Okay, so let's find him.
Are you Dutch?
No.
Okay, so I find you, and are you Dutch?
No.
Okay, and I'll just find the next person. And are you Dutch? Yes. Okay, so bye-bye.
Wait, you can't just say bye-bye. Okay, if you free him, let's try that. Okay, Dutch, you're free. Just drop it. Okay, and now let's go back to the start and let's give a ticket to Nadine.
Okay, then I'll just find the person you connected to and find the person.
Wait, but Dutch is gone. We freed him, so there's nothing here. We get a seg fault, right? We destroyed memory. We don't have access to that anymore. We're ruined. Okay, start over. Dutch, go back. Okay, remember we were trying to set Dutch free, but without destroying our queue.
So just first find Dutch. Are you Dutch? I'm not. You're not. Okay. Are you Dutch? Okay. And then are you Dutch?
Okay, good. We're partway there. We've found him. Now what's the next thing we have to do? What cable do we have to change in order to set Dutch free?
Maybe just connect this green cable just to just destroy the red one and use the green one.
Okay, so let's slow down. Let's put the red one back for a second. That's the right idea, but let's do it a little bit more methodically. Okay, Dutch, maybe connect the red one to the other port. Like I gave 2 slots on the, yeah, there we go. Okay, so first, if we want to move the green one, we've got to figure out what node it's going to end up at, right? So what's the first step? We need to know where the green arrow is going to go. Sorry, where the green cable is going to go. Okay. So where's the green cable going to go?
I need to find the next person after Dutch.
Yeah, so we ask Dutch.
Ask Dutch, who are you connected to? And I find you.
Yep, and now we're still keeping track of Dutch because we need him for a second. What do we need to? I need
Dutch's cable.
But who is actually in charge of Dutch's cable? Josh. Okay, so we're going to need to keep track of more people. We're going to need to keep track of Josh, Dutch, and
Shihun. Yeah, you can call me Chen.
I'll work on it. Yeah. Okay, so we're keeping track of all of them. Now let's give instructions to the right people. Okay, so the cable belongs to Josh. So what are we going to ask Josh to connect his cable to?
I need Josh to connect your cable to Chen.
Yep.
This cable and connect.
Well, the red cable is still plugged in at the moment. All we've done is ask Josh to attach his. Yep. And now what can we do with Dutch?
I need to remove the red cable.
Does it matter if we actually remove the red cable, or can we just set Dutch free? This is Dutch's cable.
Just set Dutch free?
Yep, okay, drop it, go ahead. And now let's see if our list still works.
Okay. So I'll first find, so now I'm
trying to give a ticket to Nadine.
So first, are you knitting? No. Okay, so I'll go to Josh, and are you knitting? No. Okay. I'll go to, are you knitting? No. Okay, and then, are you knitting? Okay, so here's the ticket. And
Congratulations, you have just made a linked list. And can we have a round of applause for everyone? Thank you to our lovely volunteers for today. I do have something to confess, though. Unfortunately, there are no Taylor Swift tickets. I know you're all very disappointed, but if you want to start a GoFundMe to give 1 ticket to a classmate, I'm sure that's something we can do. Okay, thank you very much, everyone. And so when we're about to go into the code of a linked list, and the way to get your head around it is when you start coding up the linked list, think back to this example here. Instead, indeed, maybe even draw it out. Draw out a picture, and you don't have to remember the names of all your classmates, although that would be lovely. But draw a picture with the nodes. Maybe use a circle to represent everyone, and an arrow to represent the pointers that they're going to use to connect one to the other. And now we know something about pointers in C, unlike in our example here where we could go back and forth along the cables. In C, our pointers go one direction. They go from the variable to the place that it's going to. So remember to draw your arrows at starting at one place and going to another place. So conceptually, we're all right now. We've got the idea of kind of how this works, how to add things, how to remove things, why we might want to use it. Wait, why did I want to use a linked list again? What happened when I used an array? What happened every time I removed something from the front?
It was too costly.
Yeah, it was costly. Nick, what did I have to do every time? Yeah, I had to do all this copying. So every time I removed someone from the front, I had to copy the second into the first place. I had to copy the third place into the second, the fourth into the third, et cetera, et cetera. So a linked list was much more efficient because even though when I wanted to add something, I had to go all the way through it, when I wanted to remove someone from the front, it was pretty simple. I just take the thing out from the front and, well, I move the pointer to the second thing, and then I move the first element and do whatever I want with it. So this gives us an intuition into why we want them. And this was our linked list. And here I have two of my wonderful research assistants who helped me lay tape over all of these regular power cables. This is just electrical tape, and we spent about 40 minutes winding it round. OK, so we did our array test. We did our pointer-based linked lists. What ingredients do we need to actually make this work in C? We're going to need a few things. Where did I put my clicker? Mysteriously disappeared, but that happens. Oh, there's the clicker. We need a few ingredients in C to make our abstract conception of a linked list work. First, we need a pointer, and we're going to need to contain the pointer in some kind of object or some kind of structure that has room not just for the pointer itself, that's going to point to the next object, but that also gives our object some kind of data associated with it. So in our example down here below, the associated data that was associated with everyone was their name. So we'd go ahead, and if we were looking for Nadine, we'd start at Oliver, and would say, what is your name? And then if the name wasn't Nadine, we'd say, and what is the pointer that you have access to? And we're going to call that the next pointer, because it goes to, obviously, the next item in the linked list. Now, can anyone think of, who doesn't already know the answer from having more experience elsewhere, can anyone think of a way in which I could make the add to the back operation much faster? If Nadine walks in last, what is a way that I can quickly add her to the end without having to go all the way from the front to the back? Do you already know the answer, Joseph? OK.
Could you go to the end, the current end, and then add Nadine, add a pointer to Nadine at that point?
Yeah, but to get to the end, we had to start at the head and go follow, follow, follow along. What if I tell you that you can have an extra variable? Junji?
Yeah, just like you at the start, you have a point to the start. You can have another set is at the end, directly point to the end.
Yeah, so that's the trick here. So I had this pointer over here that Leo had that pointed to the very start. There's nothing to stop me from creating another pointer that points all the way to the end. I can have two of these, and the main part of my program can have the two pointers. One pointer over there controlled by Leo that points to the start, and one, let's say, controlled by Emmeline that points to the end over here. And we'll see perhaps on, well, I guess we're off for Anzac Day, but we'll see hopefully on Wednesday a way to do this and have two pointers at once. And this will allow us to get around that extra step where we had to go all the way from the front onto the end. And I would encourage you, as like an exercise over the long weekend, try drawing out the steps of how it would work to add and remove things and what you'd have to do to both the head pointer and what we call the tail pointer in order to make this work. So we also need, other than our pointer, we need a data field in our struct to actually give people their names or whatever it happens to be, the data that we want to store at each location in our list. So this is what it looks like. This is all you really need to make a linked list. You need a bunch of nodes, and each node has data, and each node has a pointer to the next element. So one thing you'll notice here is that inside this struct node, I have a node T type. But the node T is this thing that I was trying to make in the first place. So this doesn't seem great. This is one of the problems in C. Remember, you can't use something before you've defined it. This gives us the problem of how the compiler knows what the type of A is before it's finished processing A, because we're trying to create a node within inside a node. In fact, we'd call this a recursive data structure because it refers to itself inside itself. A node points to another node, so when we define a node, we have to say what the pointer type is, and the pointer type for a node is a node. Okay, so that gives us a bit of a problem, but don't worry, the designers of the C programming language thought through this. And so what we can do is we can add a prototype or a forward declaration of the type, just like we do with functions, and then the compiler knows to look for the definition later. So we're going to say that a node T is this node type, and then we can use it when we actually declare the structure. OK, everyone got the photos they wanted? What about ending the linked list? How do we end a linked list? Okay, Nadine, could you point me towards what was after you in the list? Nothing. Okay, and what is nothing in C? Null, right? 0, null. That's how we end the linked list. We simply have an item at the very end that points to 0. And if we go along and we check what the pointer points to, and we see that the pointer is pointing to 0, we can say we're at the end. What about iterating through the linked list? Someone remind me how we did that. Michael?
Yeah. You start from the beginning and iterate linearly.
Okay. Start at the head, and then what did I do?
Step through each element until you reach the element you want.
And let's go back to our code. So if our code is, has this next pointer, what do I ask each node for?
What is the next point?
Yeah. So it would be node.next, and I'm at the next node, node.next, node.next, node.next. When do I stop?
When you reach the element you want, or at the null point when you reach it.
Yeah, so if I'm now at the very end of the list here and I see that I'm pointing off into null or off into 0, then I'm done. So we've got iteration, and this is what the code for it looks like. While the pointer that we're currently looking at is a valid one, while it's not 0, process whatever the data we want, and process is just some function that I'm making up here. This could be, process could be the function to give someone their Taylor Swift ticket. It could be the function to add the number to your sum of all the numbers in the linked list, whatever you like, that's operating on the data. And then you set this pointer, you change its value. Instead of pointing at the head or at the start of the list, we're going to change it to point to whatever the next things, whatever the current thing's next is. Adding someone to the front of the linked list, pretty easy. This was one we actually didn't do before. What we did was removing from the front and adding to the back. But now moving away from the queue to a list where we allow ourselves to do whatever we like. Now we have to have some way to push something to the front of the list. And this is the word we use, push, which means push everyone back and add something to the very start. So we create a new node. Let's call this new. Let's malloc it because we need memory for it. Check that the malloc succeeded. And our function is going to take an input, which is stuff. Stuff can be the name of the person in this case. So we set the new node's data to be stuff. And then we set news next pointer to point to what was previously at the front of the list. So it was Oliver at the front of the list. And if now Nadine comes along, and Yuvani, do you want to stand in for Nadine for the moment? Yep. Yeah. So Yuvani comes along and wants to be at the front of the list. And Oscar, do you want to hold up my head pointer for me? OK. Currently, pointed at me. Yuvani, you're away at the minute. OK. I am the head of the list. Now Yuvani comes along. We first set her up with the whole stuff over there. Then what we do is we've set her up, and now we have this command at the bottom on line 7 there, new next equals p. And so what this would be equivalent to is she controls the pointer, and I am the next element, because I am the input node, I'm the prior head. And Oscar is still pointing to me, not to Yuvani. But what I'm returning from the function, who am I returning from the function? Me or Yuvani? Just say it out loud. Yuvani. Yeah, we're returning Yuvani. She's the new one. And so what I can do is in the main function that actually controls what the head is, I can set head to be whatever the function returns. Yep. And that's how that one works. OK, let's stay poised just in case we need you again for a minute. OK, pop is removing one from the front of the list. So let's try this one out. We have the head of the list, which is our p, and we're going to have another variable old. And what will I do to mark out old? We'll use the police helmet to mark out old. So first thing we do is just create this old pointer. We haven't done anything with it yet. Next, what we do is we assert that the input head was valid. That's our value p. Old equals p. So you are the current head. Wear the hat. That is our old. P equals p dot next. Now, Oscar, that's you.
Yep.
P equals p dot next.
Oh, OK, I thought we were waiting until the return. Sorry.
No, p equals p dot next.
Yep.
So follow along.
Excuse me, what are you pointing to?
Yep, pointing to me. And now what we can do is we can free old, so drop it, and now we return P. So we return this new value now. So Ivani is free to go, and I'm the new head of the list. And we're returning that value so the main function knows what the new head of the list is. And this means that when we actually use this pop function, we have to do list equals pop list, because list is referring to the head of the list, and we want to update what the head is to the new head, because that's what pop gives back. Now there are a few different ways of writing the code. You can do it so that the pop function actually does change head itself, but that code gets a little more complicated. So this is the version we're going to give you. And in fact, throughout a lot of this course, you won't be expected to write these from scratch, although you should know for the exam. We'll actually give you a file called listops.c, which has all of this code ready for you to start experimenting with. OK, I think that is enough for you two. Oh, sorry, I'll take that back. Thank you very much. Appreciate the impromptu volunteering. OK, so this is just referring to the fact that we have to make list equals pop list, because we want to update the head in the main function to what our new head is. Now, as I said, there is an alternative. Can anyone think of a way that we might be able to modify what the head of the list was inside the main function? How do we modify something inside the main function inside a subroutine that it calls inside a subfunction? I can think of we learned something this semester about how to modify something that was in the main function inside another function. What was it? What was that, Max? Pointer. Yeah, we could use a pointer. And the head to the node is a what? It's a pointer to a, well, let's go back for a second. OK, the head is a, what type is that? The type there. Node T. It's not a node T, it's a node T. Yeah, so the head, the variable for the head is a node T pointer. And if we want to change the value of the node T pointer inside a subroutine, what do we need to make? A pointer to a pointer. So this gives us our solution. We could use a node T star star, a pointer to a node T pointer. And then if we modify this quite carefully, we can actually change what the head of the list was in the main function. I wouldn't worry too much about this. This is the more advanced version of the linked list. Just focus on wrapping your head around the basic version. But you should know that this is how it works, and B, it actually is possible in the C programming language to have all these functions that correctly modify the original head. Yes, Ruben?
So does this one modify the list so the head points to the next one and also gives you the first item?
Yeah.
So like in Python?
Yeah, this is like, that's actually a really good point. So Ruben said, is this function like it is in Python, where if you call pop, it gives you back the value of the thing that you popped, and also changes where the start of the list is. And Ruben's totally right. This version of the function is returning stuff at the bottom. So it's actually returning the data, and it's relying on this pointer to a node T pointer to change the original data structure. Now, one thing that I kind of glossed over a little earlier was that I was aiming to make a queue, but I ended up with a list. And this is, again, drawing on the idea of abstraction. We have a tool that is more powerful, our linked list, than what we necessarily need to make a queue. But by constraining ourselves and by saying, you know, I'm only going to remove things from the front and put things in at the back, I can start thinking about it in a different way. Because a linked list is one thing, but a queue we could implement either using a linked list or by using an array. They're conceptually different ideas. Even though you can make a queue out of a linked list, you can also make a queue out of an array. Whereas a linked list is a lower level data structure that gives us more ability. So we have the power to think about our linked list in lots of different ways. We can think about it as a queue, or as we'll see soon, we can also think about things in terms of a stack. But we'll get to that a little later. So here is what we were just answering. What is the value of list after the call? The value of list is whatever the new head is, because we have, in this case, modified the actual head of the list through our double pointer sequence. OK, so why are we using malloc in this context? I'm a little confused here. Why am I using malloc? Yeah, I've forgotten your name, sorry. Haruki.
Yeah, it's in the stack, it's
That's kind of true. So that's sort of true. So if if I have these functions and I create my node on the stack, then the node will get destroyed as soon as I leave that function. But let's say I put all of it in the main function. I'm just going to do everything I want to do in the main function. Why do I still want to use malloc? Okay, let's say we had everyone in our linked list except for the very last person. At this point, we know who that was. And then she walks in late. Why might I want malloc? Yeah, to expand, because I don't know how many people are going to come through the door. On any given day, the number of students in this classroom varies pretty wildly, and I don't want to have to set aside room for all 455 people. Instead, what I could do is I could just set aside room for the first person, and then knowing that students filter in slowly, add them one at a time by using malloc. So malloc allows me to dynamically decide how much memory I'm going to use. Or if I wanted to use kind of our doubling strategy from before, I could create 50 nodes ready for the students as they come in. It's probably not the most efficient way to do it, but I could. And then as each student comes, I could slot their name into the list. And then when I get to the 51st, I could double it again. But if I really know that I'm going to have this like 50 student block at the start, maybe I should implement my, my queue using an array instead of a linked list if I know that I'm actually going to have 50 ahead of time and that number's not going to change. And so the data structure that you choose to use, or the data structure that you choose to use to implement your abstract data structure should be contingent on what you know about the processing you're going to have to do. So if you know that you're going to have a fixed number of people and all you're going to have to do is remove one at a time and you're not going to have to add any to the end, then maybe you could use an array. And in fact, we can be clever. Let's say our array starts at 0 and we know that our head is at 0. If we know that people aren't going to be coming in at the end and all I'm doing is removing something at the front, then what I could do is I could say the head of my queue is at 0 in the array. And then when I give Josh's ticket away, or Oliver's ticket away, what could I do? Yeah, Junji says I could just say that again.
The head comes to 1.
Yeah, I could move the head up to 1. And so now I'm just ignoring that 0th position in the array. And now I can take the first thing out and give them a ticket. Now this was Josh. Move up one more space. And now my head is at position 2 in the array. And I can just keep track of where we're up to. And once I've given my 49 tickets away, that's it. So determining what data structure to use, again, depends on your use case. Both of these ways are valid ways of making a queue, and which is the better way depends on your scenario. So are you going to have an unknown number of things coming in and leaving? Are you going to just have things leaving? Are you just going to have things coming in? Is there a fixed amount? Is there a large amount? Do you care about the amount of computation power you use? Because remember, to copy things was expensive, but also to go down and traverse the linked list was also expensive. So which of these scenarios better corresponds to your particular case? So which 2 functions do we need for a queue? Just remind me. I only needed 2 of them. There were only 2 things I could do with a queue. Oh, no, that's a C function, but abstractly thinking, we needed to do 2 things. Yeah?
Push and pop.
We needed push and pop. We needed, or another way of saying that, we need to be able to insert things at the end and remove things from the front. OK, and as our final thing for today, let's talk a little bit about stacks. So you can think of these just as a pile of pancakes. What 2 operations can I do with a pile of pancakes? Jaslyn. Yeah, time to wake up. If I have a pile of pancakes and I'm cooking up pancakes, what can I do with my stack? I'll have to speak a lot louder than that. So I can pile them up. I can put 1 pancake on the top. What's the other thing that I can do? Well, if all I can do is pile pancakes up on top, has anyone ever had a pile of pancakes before? Did it ever shrink? No, it just kept getting larger and larger. What's the other thing we can do with the pancakes? We can eat them, right? But assuming that we are looking at reasonable sized pancakes, you're probably going to eat the top pancake first and not the bottom pancake first. I'm sure that's a difficult way to eat them. So there are 2 things we can do with our pancakes. What are they again, Jaslyn? pile them up and take one from the top. So this gives us our two operations: insert at the start and remove from the start. So if the start is the top of the pile of pancakes, what we can do is we can add a pancake on the top and take that top pancake off. Or we can add two pancakes on the top and remove the top pancake and the top pancake. Just like thinking of our towers of Hanoi, you can imagine that as a stack as well. We're stacking blocks up, and when you have blocks stacked up, you have to take the top block off first before you access the bottom ones. So we're going to reserve our Tuesday lecture, or our Wednesday lecture, for a number of code demos, looking at all the different ways that we can do some of these elements in C, seeing some common mistakes we made. And with that, have a wonderful Anzac Day, and I will catch you in just under a week. Thank you very much.